And now, a little lesson on superposition of waves. When they combine together, when two waves interfere with each other, what happens? Well, it's really easy to answer the questions. The medium itself, which is being disturbed by each of the individual pulses or waves, whatever it is, those medium displacements just add. And they add like vectors or algebraically, adding or subtracting from each other. Let's see how that works. It works as follows. We're going to have a before, during, and after. So before, we got these two pulses coming at each other. Here they are in both directions. And here is during. I'm showing the dotted lines because if we take the left one and the right one, moving to the left, once they're on top of each other, superimposed on each other, they just add. The displacements add. And if we add those two displacements, this is what we get. If we add the displacements at each point here, this plus this equals that, this plus this equals that, etc. Isn't that cool? Moreover, if you could take high-speed photography of this and investigate it very carefully, you would find out that the medium at the moment of superposition of those two pulses is not moving. Isn't that something? Now, where's the energy go then? Oh, it's in the stretch or displacement of the medium. It takes energy to do that. So in this case, it's all potential energy. There's no motional energy. It's potential energy. And then, this is kind of surprising perhaps, a moment later, you might have investigated this already. Suddenly, there's the original pulse moving to the right and the one to the left. And guess what? They're unaltered. They sure got altered when they were interfering with each other, but then they passed right through each other, and there they are. That's kind of a little surprising. You would think that after interfering with each other, they would really mess each other up, but not so. Next, let's look at two pulses going, oriented opposite each other. So this isn't going to be constructive interference. This is going to be destructive. And guess what happens to the displacements? Well, here's the displacements of each one. They're superimposed on each other. They add like vectors or algebraically, so they cancel. I'm given a situation where the two are equal size but opposite orientation. And when we add these together like that, guess what we get? That's right. We get an undisturbed medium. So while they're on top of each other, the medium itself is not displaced. It's just straight across. That's perhaps a little surprising too. Now it all happens really quickly, so you got to be really watch carefully or have high-speed photography, to do that, which is not so hard these days. Anyway, but here is maybe something that's surprising. Even though the medium is undisturbed, it's not, in terms of displacement, at that moment, is moving very quickly. In fact, this is the direction of motion on the right side and on the left side. That's the direction the medium is moving. And that's certainly understandable, right? If you think of any kind of motion, and this is the equilibrium or zero, like a pendulum swinging. When it reaches its equilibrium position, it's moving very fast. All right, even though it has no potential energy, but it has all this kinetic energy then. It's kinetic energy. That's what it has. And once again, those pulses pass through each other and continue on and look the same as they originally did. Surprise, surprise. Let's take a big pulse and a little pulse, both erect or right side up. When they're superimposed on each other, I'm showing them as dotted lines, just add the two together. Well, over this distance here, it's just the big pulse. That's why I've already recreated that. And this little part here has just the big part, so we can put that in there. Now, the rest of this, we have to add these little displacements onto this, and when you do that, you get something like this. So if you could see it in detail, you'd see this little pulse being kind of maybe looking distorted a little bit, but traveling over or on top of the big pulse. So it does that, kind of rolls around it, wraps around the whole thing, and then, whoop, there they are. They move along, again, undisturbed. So that seems kind of cool to me. So are they altered by the interaction? Well, gee, we've certainly answered that. No, they're not, for some reason. Rather, they actually just pass through each other. But while they're superimposed, can we tell what the original pulses looked like? To answer that question, I might draw your attention to this. You know, while they're superimposed, we got a flat line medium. We have an undisturbed medium. Can you tell what the original pulses are from this? Actually, couldn't this pulse here be really little and the other one really little? You get the same thing, or really big on this side and really big on this side, of equal size, opposite orientation? Yes. So you cannot tell what the pulses looked like from that algebraic superposition. But afterwards, you know what they look like because they pass through, and oh, that's what they look like originally. So what's the result of superposition? It's the term that we define as interference. Interference is the superposition of waves. It can be constructive or it can be destructive. And that is a pretty interesting little story.